recording.
Okay. I did hand out the next homework, although if you look there, it's not due for a while. The 20 Friday the 28th, so it's due. That would be yeah, that would be a week from Friday. Yeah, due a week from Friday. But I thought I'd just get that out there for those of you who want to get started on that. Okay. So what we're doing here is, so Jacob, you didn't see this then on Monday. We're talking about double integrals. We're now in the next unit. So we're continuing we'll be talking about functions with 2 or 3 variables. And what we are evaluating here is and 15.1 talks in general about how you construct a double integral. And I've got that on, you can look at whatever parts of the video you like for that. But 15.2, we get into more the nitty-gritty of it, into what are called iterated integrals. And we did an example, and so I think I want to just start out with an example, again, just to illustrate what we're doing here. So evaluate this. Now we have a double integral. We have integral from 1 to 2, integral from 0 to 3, and then we have our function. In this case, it's x squared y. And then we have dx, and then we have dy. All right. Basically, what we have here is an integral within an integral. All right? You got to change these today. All right. So what you want to do here is work from the inside out. Okay? Work from inside out. So the inside integral is this one right here, 0 to 3 x squared y dx. Now, this resembles partial derivatives. We have a function of 2 variables here, but we're only integrating with respect to x. So x varies, in this case from 0 to 3, but y is treated as if it were a constant. Okay, so it's just like with partial derivatives. Y is treated as a constant. All right. And so we get the antiderivative treating y as if it were a constant. So y is going to just stick around, and then we get the antiderivative of x squared, which is x to the 3rd over 3. All right. Okay. And then we have our 0 to 3 here. Now this is x equaling 0 to x equals 3. I think it's very helpful to put that little bit here, x equals, so that you remember it's x that you're going to be plugging in those values for x. And then that's all still inside our outer integral 1 to 2 dy. Okay. So now let's plug in the values here. First of all, x equals 3. And then, well, x equals 0, of course, we'll just zero things out. When we plug in x equals 3 here, we're going to have 3 cubed over 3, which is 3 squared. So we're going to end up with 9y. And the 0 is just going to be 0. So that's what we get from there, from the inside integral. And then, don't forget, we have our outside integral, 1 to 2, 9y dy. And now this time, y varies from 1 to 2. X now is treated as a constant. Of course, in this case, well, guess what? There isn't any x, so we don't even have to worry about that. Okay, we get the antiderivative of 9y. That's 9y squared over 2. And then we're evaluating it from 1 to 2. All right, and then we just plug in our numbers. That's going to be 9y squared over 2 minus 9 1 squared over 2, and we end up getting what? Let's just keep it all over 2. This is 9 times 4, 36 minus 9 all over 2, so that's 27 over 2 is our answer. Okay? And so that's the answer. Now, in this case, we first started as we evaluated with respect to x, and then we evaluated with respect to y. All right. We can basically work the other way, and we're going to, did I do that the last time where, let's see, let me go back to my first 2 pages here. Oh yeah, actually here. This is actually, let me just put up here what we had done the last time, and let's compare this then. The example we did the last time in class was basically the same example, except we switched the order in which we integrated. Same function, x squared times y, except last time we first integrated with respect to y from 1 to 2, and then we integrated with respect to x from 0 to 3. So same limits of integration, same function. And the answer that we got the last time was 27 over 2, the very same thing, okay? So basically, if your function is continuous, it doesn't matter what order you integrate in, okay? Just like when you do partial derivatives, it didn't matter if you took the partial derivative with respect to y and then took the partial derivative with respect to x, or did it the other way. Took the partial derivative with respect to x, and then took the partial derivative with respect to y. You got the same answer. So what I want to put here then in conclusion is we see that integral from 1 to 2, from 0 to 3 of x squared y dx dy equals going the other way, from 0 to 3 to 1 to 2, x squared y dy dx. Okay, same answer, different orders of integration. All right. All right. Now the thing is, what's the connection between this iterated integral that we're doing here with what we talked about in the last section? And this next theorem gives us the connection, okay? It's called Fubini's theorem. So let me write this down. We're assuming that our function of 2 variables is a nice continuous function. And so we're assuming that it's continuous on a rectangle R, where x goes from A to B, and y goes from C to D. So that's notation that we introduced the last time for those of you who weren't here then, that this means x is going from A to B, y is going from C to D. If we look at this, x going from A to B, y going from C to D, that's why we call it a rectangle. That whole area there is our rectangle. So let's go back to the theorem. If f of x, if fxy is continuous on this rectangle, then the double integral over the rectangle of fxy dA, and this is from notation from section 15.1, is equal to our iterated integral, is equal to the integral from A to B, C to D of fxy, let's see, C to D would be y first, dy, and then x next, or just reversing the order, integral from C to D, A to B of fxy dx dy going the other way. So therefore these integrated integrals give us the answer that, remember in the last section we were adding together all these heights and areas. Well, you don't do that. You just apply the Fubini's theorem to get your double integral. All right. So let's just look at some examples here of this. Example, evaluate double integral over rectangle R, x minus 3y squared dA, where this is our rectangle, R is equal to 0 to 2 times 1 to 2. Again, that's the x values and that's the y values. All right, well, we know we can do this just by doing the iterated integral. So let's set it up here. We can go either way. I think I'm going to go here with the y as the outer one, so 1 to 2, and then from 0 to 2. Here's our function, x minus 3y squared. Now 0 to 2 is the x, so that's, I'm going to put the dx on the inside. 1 to 2 is the y, I'm putting the dy there on the outside. So be sure that you don't mess up those limits of integration, okay? All right, so we're going to go from the inside out. So we're going to start with that inside integral with respect to x. So with respect to x, we're going to treat y as a constant. All right. So the first term is x. Well, that antiderivative of that is just going to be x squared over 2. Now, when treating y as a constant, what's my antiderivative going to be of minus 3y squared? Right, minus 3xy squared or minus 3y squared times x, however you want to look at that. Minus 3y squared x. And then we have to evaluate this. Now this is from x equals 0. Upper limit is x equals 2. And then remember, this is all inside my outer integral 1 to 2 dy. All right. So let's plug in the upper and lower numbers. The nice thing about 0, of course, is that things usually just disappear with 0, so that's a good thing. So let's plug in the 2 here, and we're going to get 2 squared over 2, which is 2, and then minus, we're going to have 2 for x, so that's minus 3 times 2, that's minus 6y squared. And then, of course, 0 on the bottom will just be 0. And so that's what we get from the first integral, and now we keep that inside of our second integral from 1 to 2 dy. All right? And now we notice we just have y's now, so I just take the antiderivative with respect to y. So 2 is going to become 2y. And minus 6y squared is going to become minus 3, let's see, 3 over 2, minus 2y cubed, right? Yeah. 6y cubed over 3, minus 2y cubed. And we're going to evaluate that then from 1 to 2 and get our answer. Are we following okay so far what I'm doing? So 2 times 2 is 4, minus 2 times 8, so that's minus 2 times 8 is 16, and then minus, and now we plug in the 1, 2 times 1 is 2, minus another one, 2 times 1 is 2. Is that right? Yeah, right. Those will just cancel out, so I end up with just 4 minus 16, or negative 12. That's my answer. Okay, we all right with that one? course, I could have done this one. There's no problem. I could have just chosen to do this one just with the other order of integration, and I would have gotten the same answer. Okay, now sometimes you really don't have a choice, really, of deciding, hey, I'm going to integrate first with respect to x and then with respect to y, or vice versa. In other words, I could do it either way, so just toss a coin and I'll do it either way. Here's an example of where you don't have that luxury of just choosing which way to do it. Evaluate the following. Double integral over R of y. Well, this one we do have a luxury, but we pay a price. Y sine of xy, x times y, where the rectangle is x goes from 1 to 2, and y goes from 0 to pi. Okay, so let's say let's just say we decide, okay, I'm going to integrate first with respect to y and then with respect to x, right? So I decide, let's do it this way. Okay, so I'm going to first do y, so that's 0 to pi of y sine of xy dy. And then second, remember we go from inside out, then second, I'm going to go x from 1 to 2 dx. All right. Now we can do this. However, look what we've got here in our integrand here. Y is, remember, right inside here, y is the variable. Y goes from 0 to pi, and x is treated as a constant. Okay, so what technique learned very early in Calc 2 do we have to do in order to evaluate that antiderivative? Non-U substitution, integration by parts, is what we would have to do to get that inside integral, all right? And I'm not going to do that, because there's an easier way to do it. But I'm just going to state, okay, if we did it this way, which you can do it, you'd have to do integration by parts. Everybody agree with that? We'd have to have u equal y, and then dv equal the rest of it. Let me just put this out here. And then we'd have du is equal to dy. And what would, well, let's, remember, x is treated as a constant. Let me just put that out there. What would my b be? Would it be positive cosine or negative cosine? Negative. Okay, be negative cosine xy, but it's also going to be something else, too. 1 over x. Yeah, minus 1 over x. What's that now? Why did I do that? Okay. This is just a good little review here as to why I did that. Let's just go back to basically Calc 1. And let's find the antiderivative of the sine of 5y dy. Okay? Well, we know the antiderivative of sine is negative cosine, right? But remember that little fast trick that I told you guys to do. You could do a formal U substitution to evaluate this antiderivative, where you let u equal 5y, du equal 5 dy, 1 over 5 du equals dy. You can go through all that process if you just love to write stuff down. But the fast way is take that number that's multiplying the y and divide by it. So that's 1 over 5. You can check your answer. How do you check your answer? How do you check an antiderivative? Take the derivative of it. You take the derivative of this, you will come back to that. I'm just doing the same thing right here. Remember, we're treating x like a constant. So I'm just dividing by my constant x, just like over here, I divided by my constant 5. All right? All right, and then we have to proceed from there. And I'm going to stop right there. Let's then see what happens if we integrate the other order. So now let's look if we start with x, 1 to 2 of y sine of xy, and that's with respect to x. And then our second one is going to be 0 to pi on the outside, dy. Okay, now on the inside there, we're treating y like a constant. X goes from 1 to 2. Y on the inside is treated as constant. Okay. So now, what do we get as our antiderivative in that inside one? This is a constant. That's a constant. Yeah, just negative cosine xy is how it's going to work out. Let's just work it through. We keep our y. Antiderivative of sine is minus cosine. But then we have to divide by our number that's multiplying. And so the y's cancel out. Very good. So our antiderivative here on the inside, so let's go to another sheet here then. This is going to be minus cosine of xy. Right? And now we're evaluating that. What is it? X going from 1 to x going to 2. And then our outside integral is 0 to pi dy. All right. So plug in our values for x. That's minus cosine of 2y. And then we have a double minus, so it's plus cosine of y. And then we're integrating that from 0 to pi dy. Okay? Now, again, formal u substitution deal is nice, but you can do it faster. So what's the antiderivative then of the negative cosine of 2y? What's that?
Negative 1 minus 2y.
Yeah, right. That was just, Nikesha, did you say something? No, you didn't. Somebody, oh, Mary. Okay, is that what you, yeah, okay. Yeah, bring minus 1/2, minus cosine is minus sine, and we're going to bring that 2 down, so it's minus 1/2. Okay, and then the antiderivative of the cosine. Okay, I could do a formal u substitution, Jordan, or I could just divide by the 2 that's multiplying my y. And the antiderivative of minus cosine is minus sine. Right. I have this 2 here on the inside. Now I could do a u substitution saying let u equal 2y. All right? When you do that, you're going to end up dividing by 2 or multiplying by 1/2. So I'm just taking that number that's on the inside there, which is the 2, and I'm dividing by 2.
Oh, yeah.
Okay. Now, then the antiderivative of the cosine is the sine, plus sine of y. All right. Okay, so I got the antiderivative, and now we just evaluate from 0 to pi. What am I going to get? A lot of zeros, right? Now they're all going to be zeros. Sine of 2 pi is 0, sine of pi is 0, sine of 0, sine of 0, all 0. So my answer here is 0. One thing I want to point out here, when your answer here is 0, if you want to look at this geometrically, you can look at it as the fact that there's as much volume above the XY axis, XY plane, as there is below. And they cancel each other out. So we end up with a volume of 0. Okay, so that's one way to look at that. So I'll just write that down. There's as much volume above the XY plane as there is below. All right. Yeah, that's what we had seen on Monday. Okay, so check out the video, go through the pertinent parts there, and you'll see that it involves volume, right? Because basically what we have here, I've what we have is we've got a function of x and y, two variables. So let's look at it in this case here. Here's our function of x and y. And remember, a lot of times these things are floating around, right, like big carpets and things like that. And basically, we have our xy plane here. This integral, when we integrate over this xy plane, that gives us all the volume that is captured underneath that flying surface there. Okay? So it gives us a volume. All right. Where? Okay. All right. Let's look at another example that actually tells us specifically that we're looking for a volume. Find the volume of the solid, we'll call it capital F, that's bordered by x squared plus 2y squared plus z equal to 16. That's one of its borders. Of the planes x equals 2 and y equals 2. Those are other borders. And the three coordinate axes. And by that we're talking about x equals 0, y equals 0, and z equals 0. All right. Actually, that's that drawing here that I just put up on the board. I mean on the document reader. All right. So what are we talking about here? We're talking about, first of all, it's bordered by from x equals 0 to x equals 2. So here we have basically, let's see, how do I want to put this? Here we have our x-axis here, and it's going from 0 to 2. Now this thing is kind of goofy the way it's drawn here. We then have our y-axis going from 0 to 2. Again, it's bordered from y equals 0 to y equals 2. And then we want the bottom floor of this is going to be z equals 0. The top part of it is going to be z equaling 16 minus x squared minus 2y squared. So we're talking here about this whole volume that's captured underneath that flying surface or whatever you want, carpet, whatever you want to call it. So we have to figure out here what are our limits of integration in order to determine this volume. Okay, so we're not spoon-fed the limits of integration. Here we know we've got to have x go from 0 to 2, y has to go from 0 to 2. All right. So x goes from 0 to 2, y goes from 0 to 2. So let's start putting down some integrals here. So let's start, well, it doesn't matter in this case, we can go either way. I'm going to start with y going from 0 to 2, then x going from 0 to 2. So my inside is going to be x, my outside is going to be y, and then I put my function here. Now my function that I'm given in the problem is x squared plus 2y squared plus z equals 16. What I need to do is isolate z on one side. So I need to convert that into z equals 16 minus x squared minus 2y squared. That will give me my upper limit. My lower limit is z equal to 0. If helpful, let's get the drawing up here again here. Upper limit is going to be z equals that. Lower is just z equals 0. So let's put that function here, 16 minus x squared minus 2y squared in my integral. All right. Okay, once we've set it up, then it's a matter of just going through the process. Yes? Okay, in other words, is this what you're saying? If this right here, we were told was z equals 1, maybe? Is that what you're saying? No.
What she's saying,
Tell me, what is she saying?
she's saying,
Okay, okay. Yeah, and in fact, we're going to have a problem coming up in the next section where we have to do a little bit more work like that in order to get our limits of integration, all right?
well, what if you were equal to 1?
Well, okay, then the thing is, well, that becomes more complicated here because then we have to look at, let me forget saying that. Okay, let's just work this and let me address that after I work this, okay? All right, so here we've got our inner integral here. In this case, it's with respect to x, so I'm treating y like a constant. All right, so go term by term. 16, the antiderivative of that with respect to x is 16x. Minus x squared, that's going to be minus x to the third over 3. And then minus 2y squared is going to be minus 2y squared times x. Just adding on an x there. And then my limits there are x equals 0 to x equals 2. My outer is 0 to 2 dy. All right. Okay, so now let's plug in 2, and let's see what we get here. 16 times 2 is 32. This is going to be minus 8 over 3. Okay. And then here, I just plug in the 2 for the x, and I get minus 2 times 2 minus 4y squared. And then nicely, when x is 0 at the bottom limit, all the terms are 0. So that's what I get from my my inside antiderivative. And now that gets evaluated from 0 to 2 dy. And so we do this process. This then becomes 32y. Well, actually, let's, before I do that, let's combine our two numbers there. 32 minus 8/3. So what's that going to become? Yeah. Get them over a common denominator. It's 96 minus 8. So that's 88 thirds. And that'll be times y. And then the antiderivative of this is going to be minus 4 y to the third all over 3. And that's going from 0 to 2. Okay. And again, we're lucky with 0 because that cancels things out at the bottom. Here we're going to have 2 times 88 over 3, that's 176 over 3, minus 4 times, well, 2 cubed is 8, so that's 4 times 8 is 32 over 3. Combine those together, that gives us 176 minus 32 is 144. Is that right? 144? Yeah, I think so. Yeah. You're on a roll this morning. 48. And that's our answer. Okay? All right. Now there's one last thing in this section and then we'll take a break. Sometimes what happens is that this f of xy can be actually separated into a function strictly of x times a function strictly of y. It can happen, all right? So sometimes f of xy can be written as some function of x times some function of y. I should say sometimes rather than some. All right. Now when this happens, this double integral separates completely. Then, that double integral over a rectangle of fxy dA, I'm able to do this. I'm able to completely separate. Let's say our rectangle, again, is going to be x is a to b, y is c to d. So I can completely separate them out. This will be the antiderivative from a to b of the g of x function times the antiderivative from c to d of my h of y function. Completely separate out. So what I really do in this case is I do each of the antiderivatives, multiply the results together completely. So let's look at one example of that. You always, on problems, you always want to be on the lookout to see if the function can be separated like that. Because if it can, you save yourself a little bit of work. Okay? So always be on the lookout for this. Okay, let's look at an example. This one I think is fairly obvious. In fact, here our f of xy is equal to the sine of x times the cosine of y. I think that's fairly obvious. We've got that situation where it's a function of x times a function of y. So let's say, and here let's suppose r in this case is x is going from 0 to pi over 2, and y is also going from 0 to pi over 2. Okay. All right. So this double integral r of sine x times cosine y dA, well, I just do it this way. X goes from 0 to pi over 2, sine x dx, do that one. Y goes also from 0 to pi over 2, cosine y dy, do that one. Right. Okay, let's see what we get here for this. Antiderivative of sine is the negative cosine, and we're going from 0 to pi over 2. Antiderivative of the cosine is the sine, and we're again going from 0 to pi over 2. All right. Okay. What are we going to get here? Yeah. Yeah, Jenna. Well, okay. Now let's look at our function here. This is our function. fxy equals sine of x times the cosine of y. If we look at it in terms of what I had written up above here, this sine of x is that g of x function strictly of x. The cosine is our h of y function strictly of y. Okay? We can just get all the y stuff together times all the x stuff.
If it was like sine xy, so then xy, then we couldn't.
Right. We could not do that. So the statement was, if it were like sine xy, cosine xy, we could not split these things up like that. All right. So I think Joe said the answer is going to be 1. So what do we have? Minus cosine of pi over 2 is 0. And then we have a double minus, so cosine, so that's a 1. And then here, sine of pi over 2 is 1 minus 0. So our answer is 1. Okay. Why don't we take a 5-minute break, and then we'll get a start into the next section, 15.3. Well, what days I'm teaching? Yeah. It's either going to be Monday, Wednesday, 5:30 to 8 p.m. Or I'm not sure if they have it on Tuesday, Thursday. But it's going to be one of those two options in the evening.
I think it's on the sheet.
Oh, yes. Oh, yeah, actually, here, let's see. I had decided you were going to sit here. Oh, okay. So there you go. Okay. Since you asked for it, you had asked in that one problem what happened if C started at 1 rather than at 0. Okay. So what I was trying to figure out here is could we still have X and Y both go from 0 to 2? And we can, because basically, as long as they're just going from 0 to 2, Z is still going to be bigger than 1. All right. So therefore, we can go from, this would be our top function, 16 minus x squared minus y squared, but then we would have to back off a 1 from it because z is equal to 1. See, with the problem that we had, we didn't have to back off. All we backed off was 0, so we didn't have to put anything there.
What's always minus?
It's always what?
What's that minus?
It's what now?
Minus 1 to plus 1. How do we know?
Because I'm subtracting the top function and the bottom function from the top function. This is the top function. It's up higher. Okay? Top function subtracting off the lower valued function. This is higher up. This is just lower down. So if I'm capturing the volume, I have to subtract the bigger function from the smaller function from the bigger function. Hold. Okay, just either erase or just put it on hold. All right. Do you guys know that I also scan these things too?
If you don't, just say yes, you do know.
Okay.
What is that? What's on there?
That's a class I'm teaching this summer at a school, which isn't required, I don't think, with 3 nodes. All right. Okay. So let's move on then to let's see how far we can get here with this next section, 15.3. This is where we're still, of course, doing double integrals. But now we up the ante a little bit. Now we're not just integrating them over nice rectangles. We're integrating them over more general regions. Okay. Now, these general regions that we're going to be dealing with, there are 2 types of these regions. Type 1 and type 2. So let's start with what type 1 is. Type 1 is where the y-coordinates of the points that are inside the region lie between 2 functions of x, and I'll show you that in a diagram. The y-coordinates lie between 2 continuous functions of x. All right, so let's see what I'm talking about here. Okay, so here's a couple of examples. here we have, notice x goes from A to B, x goes from A to B, just like when we had rectangles. But now we have this curviness here. Our y-coordinates are going between, say, on the top, this function of x, g2 of x, and down below this other function of x, g1 of x. So what we're going to be doing here is we're going to be integrating our y values from here to here, from the g1 function up to the g2 function. Notice in this case, both of the ends of the region are flattened out. It does. So we can have another same type of region. Again, the y values go from this g1 function up to this g2 function. In other words, I can draw a vertical line through the region and not get out of the region. It stays right inside. But in this case, our left side is just a point, our right side is a vertical line. But the same thing, x does go from A to B. And then there's just one other picture of, again, the same kind of region. In this one, both of the endpoints here are just single points. Again, though, x is going from A to B, but my y is going, I can just draw this vertical line from that lower x function to the larger x function. Okay, that's called a type 1 region. Right. Now, oops, where are we? With type 1 regions, this is how you're going to integrate. So we're looking at the double integral over our region D of fxy dA. With this one, we're going to integrate first with respect to y. So we're going to go from the lower x function to the larger x function of our fxy, and this is with respect to y. So we first integrate with respect to y. And of course, x is constant when we do that. And then we finish it off with our outer integral. Now is going to be the x going from A to B dx. Okay? So if we see this diagram, say here, we're going to be integrating first with respect to y. Our limits are going to be, for y, are going to be, the top one's going to be g2, the bottom one's g1 of x. And then we're going to, our outer integral is then going to be x goes from A to B. Okay. Now the type 2 region is kind of the reverse of that. With type 2, the x coordinates lie between two continuous functions of y. So the x coordinates lie between two continuous functions of y. All right, so let's look at what I'm talking about with these type 2 deals. All right, so here, notice my y goes from C to D. My x values, however, vary. This is a function here of y. So that's why it's oriented vertically like this. My x is going from here horizontally over there to my higher or larger value function of x, of y. And notice that I can draw, in these types of figures, I can draw a horizontal line anywhere in the figure, and it stays entirely within the figure. Notice with this one, in this case, I could not, right over in this area here, I could not draw a vertical line that stays entirely within the figure, all right? So this is strictly a type 2 figure right here. Now here's another one where, again, y is going from C to D. This time it ends at a point there down below. Again, my x value continuously there, I can draw that horizontal arrow and all my x coordinates are between those two functions. Now this happens to also be, this one here also is a type 1 region. So we can have a region that is both a type 1 and a type 2. Because notice here, I can draw a vertical line anywhere here in this region. I think, unless there's there might be a little bit of trickiness there with that, but let's pretend it isn't there. I can draw a vertical line and it stays within the region. And I think I have one more example here of a type 2 region. Here's where it on the top and the bottom, it ends in a point. Again, y goes from C to D. My x value goes from my lower function of y to my larger function of y. Okay. Now with a type 2 region, I'm going to want to integrate first with respect to x, and then integrate with respect to y. So with type 2, when we do a double integral over the region, I'm going to first, my inner integral is going to be my lower y function, my larger y function up above. My x goes between those two, so I'm going to first integrate with respect to x. With respect to x. And of course, remember here, y is constant. And then my outer integral is going to be from C to D with respect to y. So let me kind of put these two here side by side, sort of, if I can here. I want to point something out here with these. Regardless of whether we're talking about a type 1 region or a type 2 region. What I want to point out here is this. Notice that regardless of which one we're looking at, the outer integral strictly has numbers as its limits. Here it's going from C to D, here it's going from A to B. The inside integral is going to have the function as the limits, all right? But it's always going to be that outer one always is going to just have constant as the limits, all right? The outer integral will always have constant as the limits. Will always have constant as the limits. All right. Another thing here when we're doing these problems, 99% of the time, you're going to need to do a rough, if nothing more, a rough sketch of the region that you're integrating over. Otherwise, you can set yourself up for error. And that got attention there. Yes?
How do you know if it's type 1 or type 2? How do you know if it's a function, if it's between functions of x or if it's a function of y? Okay, well, let's see if doing some examples will help shed some light on that, okay? Because this is all general stuff, all right? Let's hope that that helps. All right, so the question was, how do you know whether it's a type 1 or a type 2 region? Well, one thing, Jenna, that you're going to be able to see is once you do your sketch of the region,
you should be able to tell from your sketch whether it's a type 1 or type 2. And we're going to see that from examples, okay? So let me just put this here. Note, now not always, but almost always, you'll need to do a sketch. You almost always need to do a sketch of D. Okay. All right, so let's do a problem then with this. And one thing I will say with some of these problems is that the arithmetic can rapidly become just ugly. But there's not a whole lot I can do about that. Okay, evaluate the double integral over region D of x plus 2y dA. Now here we're told where D is the region bounded by y equals 2x squared and y equals 1 plus x squared. All right. So that's our region that we're integrating over. Okay. So what we're gonna have to do is get a sketch of what this region looks like that's trapped between these two curves or graphs. The first thing that I think anybody would want to find out is, where do these two graphs cross each other? All right? Because that's what's going to tie it up as far as giving you the region. So that a lot of times should be your first question. Where do these two graphs meet? How can I figure that out? I can do plotting, plot, points. There's an algebraic way I can figure this out. Yeah, set them equal to each other also? Is that what you're going to say, Mary? Yeah. Set them equal to each other. Here, y is equal to 2x squared, y is equal to 1 plus x squared. Well, let's just set 2x squared equal to 1 plus x squared and solve for x, okay? So let's just subtract x squared. We get x squared is equal to 1. So that means, of course, that x is equal to minus 1 or x is equal to plus 1. So those are our two x values where they meet. Well, if that's half of the picture, what also do I need besides just the x values? I got to get the y value. So how can I get the y value? Plug it in. And it doesn't really matter which one I plug it into. I'm going to get the same answer, of course. If I just plug it into this one, I'm going to get 2 times 1. So my y value is 2 for each of these values of x. So they meet at minus 1, comma 2, and 1, comma 2. All right. So let's start this little sketch here. Those are the 2 points that they meet at. All right. Then we just got to roughly figure out, well, what do these 2 curves look like? What other point is y equal to 2x squared going to go through? 0, 0. So y equals, remember, this is a rough graph. We don't have to be real precise. Y equals 2x squared is going to be a parabola starting at the origin, and it's going to go up like that. Okay? That's y equals 2x squared. All right. Y equals 1 plus x squared. What other point can we figure out that it goes through? Yeah. When x is equal to 0, y is equal to 1. Okay? So here's the vertex of that particular parabola. And so it'll then go kind of like this. It'll be a little bit Remember, they both have to meet at those 2 points, so I have to make sure that, however I draw these things, that they meet at the 2 points that I know that they meet at. We okay with that? All right. So that's what I mean by a rough sketch. Now, Jenna, is this region right here, this is the region that's trapped between these 2 curves there. Can you identify whether that's a type 1 or a type 2? Okay, either you flip the coin 50-50, you got it right. The type 1. Right, okay. Because we can draw an arrow going up anywhere in that region and it stays within the region. Okay, it's a type 1. Okay, can you draw any sideways line and will it stay completely within that region? No, it won't. It's strictly a type 1. And I'll put type 1 only, all right? So with type 1, we are going to integrate with respect to y first and then x. Okay. So our inner integral is going to be with respect to y. Now, what's my lower bound going to be? Here's where you look at your region here. My lower graph in this region is y equals 2x squared. So my lower limit of integration here is going to be 2x squared. Looking at the drawing, my upper one is the y equals 1 plus x squared. So that's my upper limit of integration. That's why you have to draw these things. And then let me put my function in, well, here's my function. It's x plus 2y. So I first do with respect to y, and then my outer one is going to be with respect to x. And notice here that x goes from -1 to +1. -1 to +1, and that's going to be my dx at the end. So again, you see that on the outer integral, my limits of integration are strictly numbers. On the inside, I've got these pesky little functions that I have to deal with. Yes? It is. Because I am a terrible drawer. That's why. All right. Well, let's see what we get here. Okay, we've got to do the inside first. We're integrating with respect to y, so x is constant. And things do get, let's see, I think things do get a little bit ugly here as we proceed. Am I correct? Yes, a little bit. All right. Okay, so we go term by term. X is constant, so what's the x going to become? xy, tack on the y. Second term is going to be 2y squared over 2, which is y squared. And now this one, okay, bottom limit is y equals 2x squared. Really, really helpful to be indicating what I'm substituting what with. Y equals 2x squared. My upper limit is y equals 1 plus x squared. And then that's all on the inside of -1 to 1 dx. Ooh, fun. All right, so let's start plugging this in and see what we get here. Okay, so on the top one, I got to plug in 1 plus x squared for y. So that's going to give me what? xy is going to be x times 1 plus x squared plus, and then I have y squared, so that's going to be 1 plus x squared in parentheses squared. All right, then I have to subtract off the bottom one. That's x times y, but I plug in 2x squared for y, so that's minus 2x to the third when I do that. And then minus again, minus, and so this is where, you know, there's all kinds of opportunities for mistakes. And here then we square the y, so that's parentheses 2x squared, and I'm going to square that. All right, that's all of that. We're then going to integrate from -1 to 1 dx. Okay. So obviously what we have to do with this thing is FOIL and distribute and combine like terms. Okay. Not too bad on this particular problem, but let's work through it. Okay. Distribute the x, I get x plus x to the third. FOIL that out, I'm going to get 1 plus 2x squared plus x to the fourth. And then I'm subtracting 2x to the third. And here I'm subtracting 2 squared. Don't forget, I got to square the 2. 2 squared x to the fourth. Okay, I don't think I made any mistakes with that. So let's go with the biggest exponent first. X to the fourth minus 4x to the fourth, that's minus 3x to the fourth. X third minus 2x to the third is minus x to the third. Okay. X squared we have next plus 2x squared, x, and a 1. So we've got, 5 different terms there, but they're all easy to integrate. And so we do this from -1 to 1 dx. Okay. We okay with the process? We may not like it, but all right. Okay, do the antiderivatives here. Minus 3x to the fourth over 4 minus x. Oh, wait a minute. Well, hold it. I did something wrong here. Thank you. Nelson, was that why you were scowling?
Yeah.
Okay. All right. I corrected that. Put x to the third by mistake there. Should have been x to the fourth, right? So let's get the right antiderivative. Minus 3x. So say something. Minus 3x to the fifth over 5. Minus x to the fourth over 4. That's going to be 2x to the third over 3. X squared over 2 plus x. All righty. And this then can, this is what I call, we've entered the hell of minus signs right here. All right? Because notice we know we have to subtract the bottom part, and the bottom part is a -1, so we've got to be careful with odd powers. That -1 to an odd power is still -1, so there's all kinds of problems here with this. Okay, let's just do it. Plugging in the 1 is easy. That's going to be minus 3/5 minus 1/4 plus 2/3 plus 1/2 and plus 1. All right. Now what I suggest with this is not trying to just do everything in one step, because unless you're brilliant, and I'm not, you're going to make a mistake. So I'm just going to put my minus sign out front here that I know is going to apply to everything that I do for this other one. Now let's see how brilliant I can be here. Now I'm plugging in -1 into x to the fifth. That's going to still be a -1. So that's going to be -1 times -3 over 5. So that's going to combine to a 3/5. Now this time, when I apply -1 to x to the fourth, that'll give me a positive 1. So this gives me a -1/4. Next one, that'll give me back to a -1. That'll give me -2/3. Now we're back to a plus 1/2 and then a -1. Ugh. Okay. Now let's combine stuff and see what goes away. Here we have -3/5 and -3/5, so that's -6/5. And I'm so bad at this, I like to do check marks just to make sure that I haven't missed anything. All right? Now here we have -1/4 and a positive 1/4. So those just go away. That's nice. Here we have 2/3 and another positive 2/3. So that's 4/3. So let's check those off. Here we have 1/2 minus 1/2, that's 0. Here we have 1 plus 1, so we have plus 2. Okay, so now we just need to combine these. The common denominator, of course, is going to be 15. So that's what? Minus 18 plus 20 plus 30. And so the numerator then combines to 32. So that's our answer. Little drop of blood on the page, so that's our answer. Okay. I think we can make it through this next one. I'm hoping. Any question about the last one? It is a bit of grunt work with this. All right. 32 over 15. All right, here we're asked to find the volume of the solid that lies under z equal to x squared plus y squared and above the region bounded by y equals 2x and y equals x squared. Okay. So, basically our D then is going to be, okay, we've got, just like with the last problem, we've got two curves on the xy plane, and we've got to figure out where they meet so we can get our limits of integration. Okay. So again, the first thing you should want to do is find out where they meet, which means in this case, y equals this, y equals this. You just set them equal to each other. All right? So what I would recommend to do with this is to get them all on one side. I'm just going to subtract 2x from both sides. So I get x squared minus 2x equals 0, and then factor out an x, and I'll get my answers. Factor an x out, x times x minus 2 equals 0, and of course I get two answers here. X equals 0 or x equals 2. So there are 2 points where they meet, and then what are the corresponding y values? Well, for x equals 0, my y value is going to be y equals 0. For x equals 2, I plug it into either one, I'm going to get y is equal to 4. Okay, so let's plot those 2 points here. Let's see, x is 2, 1, 2, 1, 2, 3, 4. Okay, so those are our 2 points. And then let's get a rough graph of these 2 curves. And let's do the second one first. Y equals x squared. Of course, we know that that's a parabola with a vertex at 0. So that's going to look something like this. It's going to curve. All right. Well, let's put it up this way too. What the heck? All right. And then y equals 2x. That's a straight line going through the origin with a slope of 2. And of course, we already have the 2 lines, the 2 points. So we just connect our, try our best to connect the 2 points. So, our region then that we're talking about is that region that's trapped right in there. Okay. So, now, question, is this region that a type 1 or a type 2 or what? Only? It is a type 1. It's also a type 2. Because, at first, it's kind of hard to do it because it's such a slim little thing there. But I can draw a vertical arrow connecting those 2 curves, and that'll be entirely within our region. Or I could go the other way. I could draw a horizontal arrow anywhere here, and that stays within the region also. So it's either one. So it's type 1 and type 2. So something like that, you can pick your poison, so to speak. You can choose whether you want to integrate first with respect to y, or whether you want to first integrate with respect to x. It's your choice. I'm going to work it as a type 1. So we'll work it as a type 1. All right. So let's see here. With the type 1, we are going, remember, we're going up like this. We're doing the x, we're integrating the y's first. So the y's, now our lower one here, the lower curve is y equals x squared. In that bounded region here, this one is the one that's lower down. So that's where I start my limit of integration. My upper one is 2x. So here it's going to be x squared lower 2x for the upper. And now I've got to put my function that I'm integrating. Remember, we're trying to figure out the volume. So there's going to be this function floating around up here. This is x squared plus y squared. That's always positive. Floating around up here, we're going to want to get that volume of that that's just over that little crescent area. So our function that we're going to integrate is x squared plus y squared. And with doing it as a type 1, I'm going to first be integrating it with respect to y. And then my outer integral, which is always going to be numbers. Okay, in this case, x goes from what? X goes from 0 to 2. All right, so that's going to be my limit for x, 0 to 2. All right, so the important thing is just getting it set up right. That's half the battle. All right, so this one here, we're going to treat x as constant. Right? So x squared is going to become x squared times y. And y squared is going to be y to the third over 3. And then, again, it's helpful to put as your lower limit is going to be y equals x squared, upper limit y equals 2x. Okay. So now we have to do the plugging in. So upper one, y equals 2x. So that's going to be x squared times 2x plus, now it's y cubed over 3, so that's 2x parentheses over 3. And then I subtract, let me put parentheses here, I subtract my lower one. Here y is equal to x squared, so I'm going to have x squared times x squared. And then plus, okay, y is x squared, so I'm going to take x squared, but now this is y cubed over 3. So the x squared is going to be cubed, and it goes over 3. So you have to be careful that you do your exponent rules correctly with this. And then this all gets integrated from 0 to 2 dx. Okay, let's simplify this thing. This is x squared times 2x, so that's 2x to the third. All right, 2x parentheses to the third is what? 2 to the third. Remember, we got to raise the 2 to the third. That's 8 x to the third over 3. All right. Now let's subtract off the bottom part. This is going to be x squared times x squared. That's minus x to the fourth. Again, let's apply that minus sign there. Now that last term is going to be x to the sixth over 3. We multiply the exponents. Okay. The only terms that I need to combine here, and this of course is from 0 to 2 dx, is the first two. Let's see, 2 plus 8 thirds is 14/3, yeah. So that's going to be 14/3 x to the third. All right. So now let's get the antiderivative with respect to x. So 14/3 times x to the fourth over 4. Notice that for the most part, the antiderivatives in these problems are fairly straightforward. We're just talking, for the most part, about polynomials. So it's not particularly tricky to get their antiderivatives. Then minus x to the fourth is minus x to the fifth over 5. And then minus x to the sixth is minus x to the seventh over 7. But 7 times 3 is 21. All right. Okay. And then this is all going from 0 to 2. Well, I can say one thing. Thankfully, it's going from 0, so I don't have to worry about the lower limits of integration. Let's try to look at the bright side of things. So let's figure out, let's plug in the 2 here. First of all, let's see. 14 over 4 is what? 7 over 2. So this is 7 over 6. 2 to the fourth power is 16. Minus 2 to the fifth power is 32 over 5. Let's see. What's 2 to the seventh power? Yep. Yeah, 2 to the sixth power is 64. 2 to the seventh power is 128. So minus 128 over 21. All right, almost there. We've got 3 fractions, got to combine. 7, 2, 5. So what's our lowest common denominator then? 35? This is 3 times 7, 3 times 2. I think what's it going to be? 3 times 2 times 5, that's what, 30. And then 7, is it going to be 210 or is it 105? It's 105, yeah. Is the 6 divide into 105? No, it doesn't. I think it is 210, isn't it? Yeah, because we have 3 times 2, that's 6. I got to have a 5 there, that's 30. I've already got the 3, but I have to have a 7, so it is 210, actually, for those common denominators. Oh, yeah, there we go. Thanks, Mary. Yeah, right there in front of me. Let's reduce this. So that's a 3 and an 8. Yeah, okay. And then with that, we just have 3 times 5 times 7. So now we just have 105. Thank you. Okay, so 105. So let's see what we have on top here. What do we have? This is just 3. So we have to multiply. I know I have a bunch of scratches over here. We have to multiply that by 35. Yeah. Where do we have here? Yeah. So I have it right over here. I have 56 times 35. Don't even think I want to break out a calculator at home. I just do it here on paper. 1960. All right. This I have to multiply by 21, right? 32 times 21. What did I come up with that? It's a minus 672. And then 21 has to be multiplied by 5. So that's 128 times 5 is 640, right? Minus 640. Yikes. Okay. All right. So we have 105 in the denominator. Let's see, what did I give when I combine all these numbers on top? Let's just tell you that we get 648. And then actually, let's see, this, yes, 3 divides into both of these. So I can divide both by 3 and I get 216 over 35. All right. Okay, so that one was fun. That's our answer, though. Okay. All right. Just the one other thing, I just want to say, okay, we set this up as a type 1, but we could have set it up as a type 2, and of course we would end up with the same answer. But let's just set it up as a type 2. We're certainly not going to go through the whole thing. But here is the original drawing here that we have right here, and let's say we want to work with this as a type 2. So with type 2 means we're integrating horizontally first, which means with respect to x. Now, let's see, this straight line here is y equals 2x. The curved line of the parabola is y equals x squared. Now, when we do it this way, we have to say, well, x is going from what to what? Yeah, right. We have to rewrite our curves. Instead of y as a function of x, we have to write them as x as a function of y. So this straight line here can also be rewritten as x equaling, when I divide by 2, y divided by 2. My parabola, which is y equals x squared, if I want to isolate x, I take the square root. And here we're only talking about the positive square root. So I don't put plus or minus. X equals the square root of y. So in this case, we look at our lower value and our upper value. Our lower value, when we go horizontally, is x equals y over 2, 2, x equals the square root of y. All right. Now, y is going from what to what? If I'm going to start horizontally, I then end vertically at my second integral. So what are my values of the y going to be integrating over? Yeah, 0 to 4. That upper value up there, this point right here was 2 comma 4. So we're going to be going all the way up to 4. 0 to 4. So to set this up as a type 2, I would be, first of all, on the inside, integrating x from my lower one, y over 2, to my upper one, square root of y. Then I put my function, x squared plus y squared, and this time it's dx, not dy. And then my y, my outer integral, is going to go from 0 to 4. Okay. So I will get the same answer here that I got, whatever that answer was, 216 over 35. Okay, just going a different direction. Okay. Okay, I think that we're going to stop there with that. We still have some more things here to cover in this section, so we'll definitely finish up. This section, 15.3 on Friday. Okay, so that'll keep us on schedule with what you can look at the calendar. Okay, and don't remember that take-home quiz is due on Friday. Although you guys, I know, have already turned it in. Oh, and is that the reason you're here? Maybe. Okay, I appreciate it.